The next thing we're going to think about is the production function. A production function shows the link between inputs and outputs. So we're gonna start with a very simple example, and consider somebody who owns an apple orchard, and we want to understand how many bushels of apple can they pick with different numbers of workers. And so we see that we've set up a sample production function here, and we see that with one worker, they can pick 32 bushels of apples, say, in a day. With two workers combined, they can pick 60 bushels total. And the graph represents the figures in the table at the left. The graph represents how much output you can get depending on how many workers you have. So one worker corresponds with 32, two workers corresponds with 60, three workers corresponds with 84 bushels of apples, and so on. So the definition of a production function then is the highest amount of output I can get for a given amount of inputs. And in our simple problem here, we're thinking about a short-run problem where we're varying one of our inputs. We hold some inputs constant, perhaps. For instance, we might hold the acreage or the amount of apple trees we have to pick from as a constant and just vary the number of workers. Right? So what we're looking at here is a short-run production function that holds the size of the acreage, the size of the orchard constant, and varies the number of workers. Those are the inputs that are variable. When we think about the shape of this production function, we can see that it's an upward sloping line. As we add more workers, we can increase the number of apples that we pick. We can also see that it's increasing at a decreasing rate. Adding the first worker adds more, collects more additional bushels than adding the sixth worker does. Now, we might want to think about why this is the case. The next thing we need to think about is marginal product. What we were looking at before was workers and total product, but it's useful to think about marginal product. And marginal product is the additional output from hiring one more worker. So when we go from 0 to 1, we go from 0 to 32 apples. That means the first worker's marginal product is 32 apples. The second worker takes us from 32 to 60, so this gets us 28 additional bushels of apples. That's marginal product is 28 additional bushels. The marginal product of labor, then, by definition, is the additional output from one more unit of labor holding all other inputs constant. So if we look at the table, you can see that when we go from worker number 1 to worker number 2, we go from 32 bushels to 60 bushels. That worker number 2's marginal product is 28. When we consider worker number 6 takes us from 120 to 132, which is 12 additional bushels of apples. You can see the formula written down for the marginal product of labor is the change in quantity divided by the change in labor. Delta, of course, means change in, so delta Q over delta L, the change in quantity over the change in labor. Understanding marginal product is important because firms are going to make marginal decisions about how many workers to hire, and so thinking about what worker number 1 did is not of much relevance when we think about whether or not to hire worker number 6. Essentially what we want to do is compare the costs of hiring each worker to the value of the output that each worker is producing. The law of diminishing marginal product is what explains the shape of our production function. It explains why it gets flatter. Past some level of workers, the marginal product of an extra worker will begin to fall, holding other inputs constant. And recall the table from the previous slide. We saw that each worker added slightly less to total output than the one before us. Why is this the case? Well, this is the case in lots and lots and lots of businesses. And it's easy to see in the context of an apple farm, but you can think about it in all sorts of other contexts. On an apple farm, we pick the low apples first. So the first apple picker has the easiest time. They can go out and pick all the low apples. The second apple picker has to pick slightly harder apples to get down from the tree. And the sixth apple has to probably get up on a ladder to pick the apples from the top of the tree to fill up their bushels. It's harder and harder and harder to get the same amount of production without more tools to work with. Now, in some contexts, it might not happen right away due to specialization. For instance, if they are climbing ladders, it might be easier for one person to carry and hold the ladder while the other person climbs. So perhaps two people working together and specializing in different areas of production might fend off the law of diminishing marginal product for a while. But eventually, unless you give workers more tools, the marginal product of hiring an additional worker is likely to fall. The next concept, the next term we need to define is the average product of labor. And average product of labor refers to the output per worker. So the formula is average product of labor is Q over L. And that's in the last column of our table. And essentially what we do is we divide total output by the number of workers. And you can see where that comes from. So for instance, if we have 4 workers, they can produce 104 bushels of apples, which is an average of 26 bushels per worker. In the graph at the right, you can see that when marginal product is below average product, it's pulling down the average. Average product is falling. If it was the case that marginal product was above the average, then it would be pulling the average up, and the average product would be rising. An easy way to think about this is if you think about a classroom, and the average score on the exam was, say, 75%. If we add a student who got 80%, that would pull the average up. If we add a student who got 60%, that would pull the average down. So when the marginal is above the average is rising. When the marginal is below the average, as it is in our graph here, the average is falling. Just a very quick reminder, in the long run, the law of diminishing marginal product does not need to hold. The problem we had here in our story was that if we added workers without giving them more trees to pick from, it got harder and harder to squeeze an extra apple into your bushel. But if we had twice as much of the other inputs as well, we don't necessarily have to have the law of diminishing marginal product. If we have, for instance, twice as many apple trees, we have twice as much low-hanging fruit. So 2 workers with 2 rows of apple trees to pick from should be able to pick twice as much as 1 worker with 1 row of apple trees. We don't have the same kind of problem when we have more of our other inputs to work with. So the law of diminishing marginal product is something that we might think of as holding in the short run, but not in the long run. In economics, we define the short run very precisely as the period of time in which some inputs are fixed in supply. In the long run, we can vary all of our inputs in production, but in the short run, we can only vary some of our inputs in production.